We study how generative adversarial networks model image semantics and thereby enable GANs to control the semantics of generated images. GANs have achieved tremendous success in synthesizing photorealistic and diverse images. To better understand how GANs synthesize images, researchers have explored various methods to interpret GANs and thus manipulate the generated images. Among the interpretation-based methods, the semantics of generated images remain less investigated. The most related work, GAN dissection, identifies units that are able to control some semantic concepts. However, those units have limited precision. In this work, we aim to answer one question: do GANs model the semantics of every pixel? Our answer is yes. Surprisingly, we find that GANs represent semantics in a linear way. When a GAN generates an image, we can extract a precise and accurate semantic mask from the generator using a learned linear transformation. Concretely, our linear semantic extractor is formulated as follows. Given a generator that maps a latent code Z into an image I and also produces a set of feature maps. The LSE first upsamples and concatenates all the feature maps into a block, and then applies a 1x1 convolution on top of it. The LSE is trained using the standard cross-entropy laws, where the segmentation labels are obtained with an off-the-shelf semantic segmentation network. Results show that the prediction of LSE displayed in the third column is close to the prediction of UNet shown in the second column. As the aim of this work is to study how GANs model image semantics, therefore, we try to prove that GANs encode semantics linearly. Our evidence for this claim is twofold. First, we study to what extent could the semantics be better extracted by nonlinear methods. For this purpose, we compared the LSE to two nonlinear semantic extractors, namely NSE1 and NSE2. We compute the mean intersectional reunion between their extracted masks and the segmentation labels. To make our conclusion more generalizable, we conduct experiments on three widely used types of GANs, namely progressively grown GAN, style GAN, and style GAN2. Each of the GAN models are trained on three diverse datasets. See the numbers in brackets. The relative performance difference of LSE to NSEs is mostly within 3.5%. Although NSEs achieve the best performance, their differences between LSEs are marginal. Therefore, it is well supported that the LSE suffices to extract semantics from GANs. Second, we try to train the LSE given only a few annotations. Given 16 annotations, the performance of the few-shot models reaches around 90%, 80%, and 70% for the three datasets respectively. It is indicated that the few-shot LSEs generalize well from the few annotations, and thus this linear formulation matches the underlying semantic embedding of GANs. The few-shot learning of LSE further indicates that the user can extract semantics from any GAN with ease. Take the car-generating GAN as an example. The user wants to annotate the wheel. The validation panel on the right shows the extracted masks using the LSE model trained with the four annotations given by the user. The LSE successfully learns to extract the semantics of the wheel for any image generated by the scan. The few-shot LSE can also enable novel image editing applications. The first application is semantic image editing. In this video, we present the editing result using the LSE trained with 8 annotations. When the user wants to edit a generated image, he can draw on the semantic mask extracted by the few-shot LSE. In this example, the user tries to remove the hair, and the editing is successful. The proposed few-shot SIE supports diverse semantic editing operations, including changing the hair shape, mouth shape, and even accessories like eyeglasses. We also built a semantic conditional sampling application. Similar to image-to-image translation, our aim is to find images that match the user-specified targets. Our few-shot SCS application is able to generate images that respect the target well.